Okay, here the something I want to explain you about the flow fields, and here you see part of a small organic Rankine cycle turbine of the volute here, the snail around the turbine. And if you look at the slides, if you look really detailed, it's a high quality picture and you can see the dirt. There was of course some oil, maybe oil particles, and you see the dirt on the wall of the snail. And this is a good indicator to visualize the flow field. Yeah, here in the region you don't have any streaks, any oil flow lines, and that's really what it's called like. It's an oil flow line. Yeah, here you see the oil flow lines, and here at the exit of the snail you see a swirl region. And what I did, I made a simulation of this model and I placed my results directly in the same angle like the volute, and you can compare now by the streamlines with the real oil flow lines, and then you see they fit really good. Yeah? Maybe refer to the slides and you can see it a bit better. Okay, here is also something we have to mention in this point. If you have, for example, a rotor and you want to visualize streamlines on this rotor, or if you want to visualize path lines, it is different if you want to visualize the absolute system, yeah, the instationary flow field, or if you want to visualize a relative system on the wheel. And you can always choose it in the program if you want to visualize the absolute streamlines or the relative streamlines. You will mention if you make rotating part simulation, it will make quite a small difference. Here is another oil flow visualization of a ship hull, and I took this picture because it's a really, I think, a really high quality matching between numerical flow simulation and oil flow line simulation on the ship hull, on the stern, or on the bow of the ship. And here you can also, they made some experiments with the same ship hull, and they put some oil into the water and got really good streamline visualizations on the ship hull. And you can compare. That's always something that is pretty good if you have it in your slides, if you compare some pictures, some experimental pictures with the numerical simulation to prove what you did. Okay, here again we have also flow fields around the ship hull, and again it's the same problem as with the wheel. You can visualize in an absolute system. Imagine you are here, you are a person at the side of the river, and the ship comes here from here. You got special visualization of streamlines. Or if you are on a relative system, if you sit on your ship and you flow with the ship, the streamlines would look quite different. And both methods can be taken as a visualization and explanation of the flow. Both are true. They look totally different, but both can be used for visualization. It depends on you, where you sit. If you sit outside on the beach or inside the ship. Okay, I don't want to tell you too much about the numerics and about the mathematical equations. I think that's a bit tough, and I show you the equations, but we will not solve it here. We want to make pictures, we don't want to get too deep. But one thing you should always keep in mind, derivation can be important, derivation of velocities. Of course, all numerical simulation is somehow, CFD simulation is somehow a derivation, and you can get decomposition, but don't make too much now about decomposition. Sometimes deformation tensors can be important. Yeah, if you have velocity gradients, you can use to construct the deformation rate tensor or the symmetry tensor. Yeah, symmetry is sometimes a topic. Yeah, if you want to force symmetry to your results, maybe you can make deformation tensors. But let's come back to visualization. Yeah, here's a deformation illustrated. You can illustrate deformation again by particles or streamlines. And let's have a short look at the strain rates. So, okay, strain rates are also used to various other calculations, for example, for non-Newtonian fluids, to visualize viscosities, or to visualize shear rates in the fluid. Yeah, and here is a zoomed out version where you visualize the strain rate. Yeah, let's say the deformation in the fluid field. Yeah, and that's a bit more complicated. And again, here you can zoom in to visualize strain rates around our ball example. Here we have high strains, here we have low strains, and that gives you also an imagination of turbulence. So often we visualize turbulence by turbulent viscosity. Yeah, that's a model constant. Okay, then we can have vorticity, two-dimensional vorticity, and we have to, or three-dimensional vorticity. It gives you also impression about turbulence. We'll come to this topic a bit later. Okay, and you can also make flow field and contour plots of the vorticity around your cylinder. So this is a vorticity, gives you an impression about gradients inside the fluid, strain rates and swirls. And vertex lines and helicity can give you also expression of swirls. We will try out this feature during the lesson. I don't want to stress the topic too much now. Okay, here's also a visualization of this type of this vorticity and of this strain rates, and it's an example. It's a big steam turbine. We have here the plates and the starter plates of the steam turbine, and what they did, how they made the visualization of the flow on the wall. They took red and blue color, placed it into the turbine, and then they could visualize the streamlines of the air near the wall by this, let's call it dirt layer, or let's call it paint layer. So this is another really good example. I like it real much. It's a blade of a turbine, yeah, and they put some ink or some color on the plate of this turbine, or here on this plate, and they used it in the turbine, and then you can see really good. Here is a high fluid flow region. Here's a swirl. It's really similar to the snail of the small ORC turbine. Okay, that's also visualization of vorticity inside a mixer. If you visualize this vorticity, we will try it out during the lessons. We will plot the vorticity around the plane. It gives you impression of swirl, and if you make this vorticity visualization, we always will take isosurfaces. So this is a three-dimensional object. It's an isosurface at the blade of a mixer. Or here again, this is also a mixer, looks a bit chaotic. And again here, if we had a movie is much more expressive. This is mixer, we have a stator, mixer, and we got vorticity inside by isosurfaces. Okay, we want to comparison between strain and vorticity. Both strain and vorticity contain velocity gradients, so they show you a difference in the velocity field. If you have low velocity regions, high velocity regions, you can compare flow fields, you can show planar shear fields, strain rates, we can visualize rotations, and we can also combine shear fields and solid body field rotations. Okay, that's a planar shear field, some solid rotations, solid body rotations combined, and we come more or less to the end. I don't want to stress too much formulas here, but I want to mention we can have integral values where we integrate over time steps or areas, or we can make mean values, and you can make a lot of different mean values. You can make area average mean values, you can make mass average mean values, you can make, there are I think 6 or 8 different mean value features, and we can also take mass flow rate averaged values. Okay, here is a picture of a moving train, and I think that's a pretty good presentation. You show the mesh, you show how many mesh points are, you have to write it down, you explain the structure of a mesh, it's a tetrahedral mesh, and then you look at the pressure fields, the pressure fields around the train, you visualize it, but you should not only make a colorful fluid dynamics. I started with this colorful fluid dynamics, that's one thing. You should also extract here hard values, pressures, make diagrams, two-dimensional diagrams by extracting values over the colorful surface. Or you can, here's an example of an NACA airfoil profile. We will come also to this airfoils in details later, but what I want to mention, you have to explain what happens, make some sketches, you have to extract lifts and tracks by formulas, you have to show the formulas to the audience, you have to explain what you want to do, and then you can plot the results and the mesh and the pressure field and some formulas, explain what you did, make some plots of the results that everyone can prove, compare maybe different codes, or okay. So, as a summary of the whole lecture, Cfd, we don't have even colorful fluid dynamics, but sometimes it's not too bad to make it colorful. You should describe your results in a good way, in a way that people like. You should make proper analysis, you should give hard values, you should compare it against measurements, make validations, and it's always good to compare different simulations against each other. So that's from my side for this lecture flow field. See you again next lecture.